Hello everyone again. Today we will be beginning with a new chapter called as motion in a plane. Before that, we have started with a discussion about motion in a straight line. So let's begin. In the motion in a straight line, basically we were discussing about when only one axis has been taken place. This time we will broaden our dimensions and let us go on to motion in two plane. So what happens in two plane? What are the aspects regarding it? We'll go with each and every discussion. So let's start the discussion directly. Okay, so new chapter starting today, lecture number 1. So I am Samir Lawankar. Let's begin our discussion. Okay, so the course outline for you first of all. So let's not go into the detailing of the course outline. So let us first start with the introduction and then we can gradually move forward with all the discussion which we need to do in this. Okay, so as the name suggests only, it's motion in a plane. So if you know, so anything which is on a straight line is basically having only one axis. If we increase the dimension to 2, then we are working on a plane, right? So plane can be anything, plane can be of any shape, right? So if you are working on this, the complete prospect of motion in this. So this is also a part of kinematics only, the kinematics word which was just added to your syllabus, or not your syllabus, basically to your dictionary in the last lecture only of motion in a straight line. So kinematics deals with these all concepts. Let us now broaden our dimension so that we can understand what are the different aspects or what are the additional complexities which we have when we try to go from x-axis only to x and y-axis. So it depends upon your conceptualization that how you take it. Let us take everything as x and y, because majorly we work in x and y only. Maybe we will take y, z or zx, etc., depending upon our considerations. So let's start with the introduction only directly, and then we can move on to the considerations which are required in this chapter. Okay, so let's start with the introduction of this and then we can move forward. Okay, so introduction. So let me start. So in the chapter on motion in a straight line, we developed the concepts of position, displacement, velocity, and acceleration. So just to revise you, what are these? So position is basically at any, let us take any coordinate space. Let me take the coordinate spaces, let's say x, y, z. Correct? If you are only and only talking about motion in a straight line, so there is no use of using y and z direction. Let us only take x direction for our consideration. If you are taking x direction for our consideration, let us take this to be the origin. We understood the concept of reference point in this. We also understood the concept of reference axis and a point of frame of reference in this. Okay, so these all concepts are explained in detail in the previous chapter only, or I may assume that you know these concepts, and then let us move forward with understanding these results. Okay, so we have this frame of reference here, that is your origin, and let us say that this is the straight line being drawn. Fine. So any position of the object can be at any location on this axis. It can be either on the right hand side direction or it can be on the left hand side direction. So this is basically the position of the object, right? What is displacement? Displacement, as the name suggests, or displacement is a path length only, but it's a vector quantity. First of all, you should remember vector. Okay, so this is the chapter in which you will understand a new subject or branch of mathematics to be supposedly, which is vector. How it is different from scalar quantities, what is actually vector, will be understood in very detail. So majority of this chapter is based upon understanding of vector one. Okay, so we will understand this when the time comes. For now, let us understand displacement. So displacement was mathematically written as equal to x2 minus x1. Okay, so let us start again. So what is displacement? Basically, displacement is nothing but it is equal to x2 minus x1. Okay, or in more general terms, it can be written as equal to x final minus x initial. Graphical form for the motion in a straight line, this will be equal to, let us say this is the value of x2, this is the value of x1, which was origin. That is nothing but equal to x2 minus x1, right? The difference between path and displacement concept were being covered in the previous lecture of motion in a straight line only. So if you are not understood, if you have not understood that concept, you can go back and just refer to those concepts. Okay. Then next thing was velocity. So what is velocity? Basically, velocity is nothing but equal to delta x upon delta t. Right, where delta x is nothing but x2 minus x1, and velocity can be positive also, negative also. Similarly, acceleration. So what is acceleration? Basically, what is acceleration is nothing but equal to In very general terms, it is nothing but del V upon del T. Again, please remember delta V is a vector quantity, acceleration is also a vector quantity, and displacement is also a vector quantity. Fine. These all things being explained. Let's move forward then. So in the motion of a straight line, in the chapter on the motion in a straight line, we developed concepts regarding position and displacement, velocity, and acceleration. So we developed these concepts of position, displacement, velocity, and acceleration that are needed to describe the motion of object along a straight line. So in the previous chapter, we were only focused about motion in a straight line. Now, we found out that the directional aspect of these quantities can be taken care by plus and minus sign. Quite evident. Let us say we take only the x-axis. If we move in this direction, let us suppose this is the origin we are talking about, or the reference point we are talking about. Then if you are going on the right hand side, we can assume it to be positive, though that is only based upon your sign convention, and either it can be negative. Similarly, if you are working with a y direction space, so if it is a reference point you are talking about, then above is positive and below is negative. Okay, so basically it is just saying that we found that the directional aspect of these quantities can be taken care of by plus and minus signs. As in one dimension, only two directions are possible. Quite evident, as you can see. So this is also one dimensional, or this is also one dimensional. Okay, so these are two different ways in which motion in a straight line can occur. Okay, so they both are not combined. They are just two different examples I have put forward. Okay, but in order to describe motion of an object in two dimensions, what does it mean by two dimensions? Basically, two dimension basically means that now you are the working of a object is not in a single dimension. It is in two different axes. Okay, so it can go in this direction this way, or it can go in this way, or it can go in this way. So any of this can occur. So this is basically two dimensions happening. So let us assume that this is x and y. So this can be explained understood as a plane. Okay, so this is a motion in a plane, and that is the complete that is the name of the chapter. Okay, so but in order to describe motion of an object in two dimensions, a plane or three dimension space. So making you understand the three dimensions here. What is three dimensions here? Three dimensions is basically x, y, z. Right, so basically let us say there is some object here, so it can move in this phase like this, right? So this is basically moving in a space. So space is having three dimensions, that is x, y, z. So we need to use vectors. Okay, so a new thing has come up. So we need to use vectors. When do we need to use vectors? We need to use vectors when we are working in two dimensions and three dimensions. We needed to use vectors in one dimension also, but that was a very easy or a basic version of use of vectors. Here, majority of the strength or the conceptualization or the calculations involved will be based on understanding vectors proper. Okay, fine. Therefore, it is first necessary to learn the language of vectors. So what is a vector basically? We will understand these all concepts in the subsequent slides. How to add, subtract, and multiply vectors. What is the result of multiplying a vector by a real number? Okay, so you know what is a real number. Okay, so any number which consists of all the whole numbers, then rational numbers, irrational numbers, etc. The addition of all the rational and irrational numbers are basically real numbers. Okay, so we shall learn this to enable us to use vectors for defining velocity and acceleration in a plane. So after we have understood the complete concepts of vectors, we will go forward and then understand the motion in a plane. Okay, fine. After this, we will understand or we will discuss the motion of an object in a plane. As a simple case of motion in a plane, we shall discuss the motion with constant acceleration. If you remember correctly, in the chapter of motion in a straight line, we introduced three kinematics equations. Please remember, those kinematics equations are only and only valid if we take constant acceleration into effect. Okay, so A is always constant, and treat in detail the projectile motion. So in this, a new concept which is called as projectile motion. Just to explain you what is projectile motion, we'll go into depth of projectile motion at the end of this chapter. So let us say that there is a coordinate axis or there is a plane xy happening, and let us say we had a ball here, and I shoot up the ball in this phase like this at a velocity v. Okay, and it is having some angle theta. So there will be a path of this ball which it will be acting upon. This complete motion. So what is motion? Motion is basically the movement of an object from, let's say, point A to point B. It is traversing from point A to point B. There is a change in position with change in time. So this is basically motion. But this type of motion is called as your projectile motion. Okay. So that was a simple definition of projectile motion. The actual physics definition will be explained when we will understand this in the later part of this chapter. Okay. After projectile motion, we will understand circular motion also. So circular motion is a familiar class of motion that has a special significance in daily life situations. We shall discuss uniform circular motion in detail. Okay. So as the name says, we will understand uniform circular motion. Okay. So what is the basics? What is the basis behind circular motion? What is the acceleration acting upon it? What is the name of the acceleration which acts upon a body moving in circular motion? These all things will be explained in detail at the end of this chapter. I think the last topic of this chapter is motion in a it's uniform circular motion only. Okay. Next thing is the equations developed in this chapter for motion in a plane can be easily extended to the case of 3 dimensions. Okay. So in majority of the chapters, when we will try to devise the equations for, let's say, 2 axes or in vector addition or vector multiplication, we will supposedly see how we can multiply it or how we can broaden our aspect to take 3 dimensions also into consideration. Okay. We may not be solving 3 dimensional cases in this chapter because it is the basis of basic of your vector, but we may understand how we can extend it and then we can directly use it in our further chapters or further higher classes. Okay. Fine. So let's start with, first of all, scalars and vectors. Okay. So please be very please listen to it very carefully because vector is a new concept for you. Okay. In starting, let us make it very, very simple and then we can move forward. Okay. So first of all, this first term which is written is scalar, right? So scalar is all the things which you have done till class 10th, everything which you have added, subtracted, multiplied, divided using the basic concepts of your algebra were called as scalars, right? So examples of scalars can be what? You have added lengths, right? So lengths were being added. In the previous chapter, you understood a concept which is called as path length, basically, right? Then what else? There was mass. There was mass we added, and there was time, right? So these all things are nothing but scalars, right? So what is the meaning of scalar? I will just put in an example for it. So let's say I have an object A and I have an object B. Okay, fine. The mass of this is 5 kgs. The mass of this is, let's say, 3 kgs. What if I say that please tell me the total mass of both objects? You will just use simple mathematical operation, algebraic operation, and you will find the answer is equal to 8 kgs, right? So this is nothing but the basic example of how we use scalars. So scalars is basically those quantities which are having only and only magnitude. Okay, now let us broaden our aspect. So now what is vector? Just a basic analogy. First of all, what was scalar? Okay, not like this. Let me explain it like this. So scalar and vector. Okay, so what was basically scalar? Scalar was having magnitude. Okay, and this vector was having magnitude plus direction. So this direction is the only and only cause which makes it different from a scalar. And that is why we need to do vector addition, which is different from algebraic additions. We will understand how we will do it, but that is the main crux of what is the difference between a scalar and a vector. Okay, so let's start understanding whatever is written here. So in physics, we can classify quantities as scalars or vectors. Okay, basically the difference is that a direction is associated with a vector but not with a scalar. Okay, so a direction is associated with a vector but it is not associated with a scalar. Fine, so this thing is also done. A scalar quantity is a quantity with magnitude only. A scalar quantity is a quantity with magnitude only. Fine, so this thing is also understood to us. It is specified completely by a single number along with a proper unit. Okay, yes. So unit is important in both of these considerations, right? So unit is the basic building block of your physics. Okay, so anything which you write, please always have a habit to write it with a unit. Okay, if the unit is not given, try to write it by using units only, so that you may have a very good habit of writing units always. Okay, so it is specified completely by a single number along with the proper unit. Fine. Examples are the distance between 2 points, as I explained, that is length, then mass of the object also, then the temperature of a body, and the time at which a certain event happened. So these all are examples of a scalar. Fine. The rules of combining scalars are the rules of ordinary algebra. So plus, minus, divide, multiply can be done very easily as we do in our mathematics or in supposedly in algebra. Okay. Scalars can be added, subtracted, multiplied, and divided just as the ordinary numbers. For example, so an example is given. So if the length and breadth of a rectangle are 1 meter and 0.5 meter respectively, so length is given to you as 1.0 meters, the breadth is given to you as 0.5 meters. Okay, then its perimeter is the sum of lengths of four sides, right? So what is the perimeter of a rectangle? It is nothing but 2 into L plus B, right? So that is nothing but equal to, so I'm just doing your simple algebraic expressions here. So this is nothing but equal to 2 into 1.5, which will give you the answer as equal to 3 meter. Please remember, first of all, this is a magnitude being added here and this is the unit being added here. Okay, so there is only a magnitude involved here. There is no involvement of direction till now. Fine. So the length of each side is a scalar and hence the perimeter is also a scalar. Okay, so please remember that perimeter is also a scalar quantity. Okay. Take another example. Let us take another example. So take another example. The maximum and the minimum temperatures on a particular day are this and this respectively. Then the difference between two temperatures is 11.4. So how is this thing calculated? This thing is calculated as follows. So basically, it is given that T max value is equal to 35.6 degrees Celsius and T min is nothing but equal to 24.2 degrees Celsius. Fine. So what is the difference between two temperatures? So that is nothing but delta T. We understood the concept of delta in the previous chapter only. Delta was basically a Greek symbol which tells you that anything which is written on delta, you just need to find out the difference of the same. Okay, so it's here delta T is nothing but T max minus T min. So it is T max. So delta is used to find out the difference of the two same quantities. The numbers can differ. So it is nothing but we are doing a simple mathematical operation of difference here. So it is nothing but equal to 11.4 degrees Celsius. So here also similarly, this is also a scalar quantity only. Okay, so this is also scalar. Okay, it is also written an example also that temperature is also a scalar quantity. Okay. Similarly, if a uniform solid cube of aluminium of size 10 centimeter has a mass of 2.7 kg, then its volume is 10 to the power minus 3 meter cube. Quite evident. How is this thing calculated? It's nothing but V is equal to L cube here, right? And its density is, how is density calculated? Density is nothing but equal to mass by volume. Okay, mass by volume is your density. So mass is given to you in the question, that is also a scalar. Volume is given to you in the question, or we just calculated basically, and therefore this is also a scalar. Okay, because length is a scalar, any multiple of length is also will also be a scalar. Mass is simply a scalar, so mass by a volume, that is basically scalar by scalar, will also be a scalar quantity. Okay, so that is the explanation being done here. So this complete slide was based upon your scalar explanation. Now I think let us move on to vector. Okay, vectors. Okay. So please understand it very, very clearly. I would like to go very slow here. Okay. So what is a vector quantity? So a vector quantity is a quantity that has both magnitude and a direction and obeys the triangle law of addition or equivalently the parallelogram law of addition. What is this triangle law of addition? What is the parallelogram law of addition? Is a concept which you will study in after 2-3 slides. So don't be hesitant about this. First, let's understand this as a definition that what is a vector quantity? It is nothing but a quantity that has both magnitude. So magnitude was basically involved in scalar also. What is the new addition here? A direction has been added. Okay, so it obeys the triangle law of addition or equivalent to the parallelogram law of addition. Okay, so that is how the definition has taken place. The next line states that, so a vector is specified by giving its magnitude by a number and its direction. Okay. Next thing is some physical quantities that are represented by vectors are, so please remember this. So displacement, we have also understood this in motion in a straight line also. Similarly, velocity, right? So as velocity is nothing but change in displacement upon time. So displacement is a vector quantity, hence your velocity is also a vector quantity. Similarly, acceleration. What is acceleration? Acceleration is nothing but your change in velocity upon time. As velocity is a vector quantity, therefore acceleration is also a vector quantity. And force. Okay, so a majority of the concept of force will be understood in the next chapter following it, that is laws of motion. So you can understand about force at a very great detail there. Just understanding you mathematical formulation of force. So force is nothing but equal to mass into acceleration. Okay, so this is one of the mathematical definition of your force, that is mass into acceleration. Because acceleration is a vector quantity, therefore force is also a vector quantity. Fine. So any vector multiplied by scalar will always be a vector only. Okay. So that thing is being explained. Next thing is, okay, fine. So now to represent a vector, we use bold face type here. So in this complete chapter, whenever you find something written bold, so that means that that is a vector being represented. Okay. So one of the ways, either you represent it like this, or either you represent it by a sign with an arrow. Okay, so that is also one of the way in which you try to represent the velocity vector. In some of the books, it is also represented like this. Okay, but generally in physical terms, so here also in some of the ways you will find it written as like this only, it's v bar. Otherwise, as it is also an example or determination of telling you the average value of the, let's say, vector, that is why sometimes I don't use it. It is depending completely upon you how to try to represent vector here. Okay, so just to change it different, so just to make it different from a scalar, we add some different representations to a vector. Okay, then so this thing is explained. Next thing is, thus a velocity vector can be represented by a symbol v in bold. Okay. Since boldface is difficult to produce when written by hand, a vector is often represented by an arrow placed over a letter, say V bar. Okay, so I say it as V bar. Thus, both bold V and V bar represent the velocity vector. So first of all, we are understanding the representation. Then we will keep on adding the different properties of vectors as the slides goes by. The magnitude of a vector is often called its absolute value. Okay, so what is the magnitude of vector? So magnitude of vector is often represented as like this. So it's nothing but mod of, so basically mod of, this is represented like this, which is equal to v. So here it is equal to v only. So let us say, okay, so I won't go into example right now, it will create confusion. Let us go with the detailing here only. Okay, so this vector is represented by a boldface. For example, as you can see, these all things are nothing but vectors. Why it is vector? Because we have made a representation that a vector will be represented by bold letters. Okay, with respective magnitudes, you have light phase, that is they are similar. A small a, small p, small q, small r, and similarly x and small x and small. Okay, so that was how the representation was being done. That was how the vector was being defined. Fine. Now let us understand two different types of vectors, that is position and displacement vectors. Okay. So to describe the position of an object moving in a plane, please remember we are now in the chapter of moving in a plane. So everything will be understood. So let us make one of the scenario that if it is default, if nothing is given about the coordinate axis, please always take it as x and y axis. Okay, so let us understand each and everything in x and y axis. We can broaden our respect to it, let's say yz or zx, if there may be a case regarding this. Okay. Fine. So to describe the motion of an object moving in a plane, we need to choose a convenient point, say O as the origin. So let us choose this as the origin here. Okay. Now let P and P dash be the positions of the objects at time T and T dash respectively. Okay. So they are just saying, let us say there was a position P here. Okay. There was a position P here. Okay. So what was this position P basically? This position P was having some value of x and some value of y. Okay, as the time went on, this value changed its position, and now this is a new position, that is p dash. So we can represent it like this, that it is having new coordinates, that is x dash and y dash. So there would have been a movement of this from p to p dash, right? Let us represent. So basically whatever is written here, let me try to explain it like that only. So let P and P dash be the positions of the object time T and T dash. So at some time T, the position was this. At some time T dash, the position was this. There was a motion happening and hence there was a change in position. Okay. So now some mathematical things would be done here. So let me clear everything. So now let us join O and P by a straight line. So as you can see, O and P are represented by a straight line here. Then OP is the position vector of the object at time t. Okay, please remember. What is OP? OP is the position vector. Okay. So what if we need to find out the position of P? To find the position of P in a 2D plane or in a plane, then we use position vector. What is position vector? Position vector is basically a plane which starts from the origin and goes to the end point. Okay, so now few things which can be explained from this diagram only. You can see clearly that how it is represented. There is a tail here, there is an arrow here. So this is how we represent a vector in on a space or on a plane. So basically that the final position is this and the initial position is this. Okay, so OP is the position of the object at some time t. Okay, so it is the OP is the position of the object at some time t. An arrow is marked at the head of this line, which is represented here. It is represented by the symbol R in bold letters, that is OP is equal to R. Okay, so how we represent it? That is nothing. OP is nothing but an R. Okay, so R, what is R basically? It will have some value of magnitude. Okay, it will have some value of magnitude. That magnitude will be nothing but the length of this value, and the direction would be, let us say this is the direction. Right now, let's understand the direction as graphical form only. Okay. Fine. Next thing is point P dash is represented by another position vector OP dash denoted by R dash. Okay. Similarly, what we did from again O, we went in this direction. So there was a tail here, there was a head here, and basically again, when we can write that OP dash is nothing but equal to R dash. Okay. Fine. So OP dash is equal to R dash. This is also been explained. Next thing is the length of the vector R represent the magnitude of the vector, right? So length of the vector R, let us say I write it like this. Let us say this is your O, this is your P. So the length of the vector R, this is the length, right? So this is the length. So this length of the vector R is nothing but the magnitude of the vector, and its direction is the direction in which P lies as seen from O. So direction is this only. So this is the direction of the vector R. Okay. Fine. If the displacement, if the object moves from P to P dash, if the object moves from P to P dash with vector PP dash. So now there's another vector here, that is PP dash. Okay. So it is P dash. So if the vector moves if the object moves from P to P dash, the vector PP dash with tail at P, please remember, tail at P and tip, it is also called as head, tip at P dash or head at P dash is called a displacement vector. So this is nothing but a displacement vector. That is how we can understand the position change in an object, and it is moved from P to P dash. Okay, so this is called a displacement vector, and so this is called a displacement vector corresponding to the motion from point P, which was at time t, to some point P dash, which is at time t dash. Okay, fine. So these all things were to be explained here. Let's move on. Okay, so it is important to note that a displacement vector is the straight line joining the initial and the final positions and does not depend on the actual path undertaken by the object between the two positions. So quite evident. This was the concept we also understood in the motion in a straight line also. So let us take motion in a straight line only for consideration. Let us take this to be the origin. There is a point P here, there is a point R here. Let us understand using the path length first. Okay, so what happens in a path length? Let us say there was a movement first in this direction till P, then we moved forward, we went backwards till R, let us say, then we went again from O to P, right? So what was the total path length covered? It was equal to 1 plus 2 plus 3, correct? But what we actually do when we find out a displacement, we start from the final position, we end at the initial position. So here in this case, we are just taking a look only on the final and the initial position, and basically draw a straight line. Let us say we go till here. So what we do, we'll just draw a straight line, and that is our displacement. Correct? Similar case is also happening in motion in a straight line also. So we just take the initial, we take the final, and we draw a straight line. So here, just because it is a vector, we will draw a straight line like this with an arrow pointing towards the final value. Okay, fine. So this thing is explained. So for example, in figure B, so now please look at this figure B here. Uh, Given the initial and the final positions as P and Q, let us say that we know that this is the initial position and this is the final position. The displacement vector is the same PQ for different paths. So either we go in, let's say, these paths. Okay, so what is the first path given? It is PABCQ. So it's PABCQ. Let us go in this direction. Or let us go with PDQ. So PDQ is this. And next is PBEFQ. So next is PBEFQ. So even if I go with either of these paths, you know that this is the initial position, this is the final position. So how will the vector be drawn? Vector will be drawn similar to the case scenario which is drawn. So that is the crux of understanding the displacement vector. Okay, so in the last two slides, what we understood? We just understood the position vector and we just understood the displacement vector. Okay. So what is basically a position vector? Let us take any position P here. Then the vector which is drawn from the origin to that point is nothing but the position vector. We can denote it by R. Similarly, let us take that this position of this object has changed from P to P dash. Then this object, when it is going from P to P dash, the vector which goes from P to P dash is nothing but your displacement vector. And this is nothing but your position vector. Fine. So that is how the consideration is being done here. Okay. Therefore, so what is the final point? Therefore, the magnitude of displacement is either less or equal to the path length of an object between 2 points. Quite evident. So what is the magnitude of displacement? The magnitude of displacement, let's say in this case, nothing but the length of this PQ. Okay, so it can be seen quite clearly from the example here only that the magnitude of displacement is basically length, and that length is either less or equal to the path length of an object between 2 points. So it is quite clear that these all paths which are being written on the we have been drawn will have a higher path length than supposedly PQ. So it can be either, so only and only when it is equal is when we move from exactly in a straight line from P to P. Rest in all different positions, the path length will always be greater than the magnitude of the displacement vector. Okay, fine. Now let us move to another property or another subtopic under vectors only, that is equality of vectors. What is the meaning of equality of vectors? Let us understand that. Okay, so one thing you should always keep in mind, anything which is always written in a bold letter will always be a vector only. Okay, so let us understand this. So two vectors A and B are said to be equal. When are they said to be equal? They are said to be equal if and only if they have the same magnitude, and the same direction. Okay. If I need to write it mathematically, what I will say that I denote this by A bar. Okay. So A bar is equal to B bar. So a denotation to write if and only if is if I write I double F. Okay. So if and only if can be written as I double F. So if and only if mod of A bar is equal to mod of B bar, so it denotes that the magnitude are same. So what does this line say? It is saying that magnitude is same. Okay, and the next thing here, the direction is same. So direction, so there is nothing to be said. You just need to write it. Okay, so direction is same. So basically, writing this line only makes you sure that the magnitude is same and the direction is also same. Okay, fine. So two vectors A and B are said to be equal if and only if they have the same magnitude and the same direction. It is not required that those both vectors should overlap each other. That is not the consideration. That is not the case here. They can lie anywhere on the space. They can lie kilometers far from each other. Only and only the magnitude of those. So basically, the length of those vectors should be same, and the direction of both should be same. Okay. Fine. So two vectors A and B are said to be equal if and only if they have the same magnitude and the same direction. So figure A shows two vectors which are equal. So two vectors, as you can see, these are the this is an example of two vectors which are having which are basically equal. How it can be equal? As you can see, the length of this vector A is equal to the length of this vector B, and similarly, the direction of this vector A is the same as the direction of vector B. Hence, it can be said that these both vectors are equal. Right. So we can easily check the equality. Shift B parallel to itself. So how we check it? So just try to let us take we can shift B from its position here. So shift B from parallel to itself until its tail coincides with that of A. So just try to put it here on the top of O here. Then the two vectors. So that is Q coincides with O. So we are trying to coincide Q with O. When we are trying to coincide Q with O, then since their tips S and P also coincide, since their tips S and P will also coincide, then the two vectors are said to be equal. Okay, so this is one of the consideration. In general terms, you cannot just put a vector and put it into that. Just it is consideration that you can visualize all these scenarios. Okay. So in general, equality is indicated as vector A is equal to vector B. So I just wrote it in the terms of bars here because generally when writing, it is not easy to make it bold. Okay, so that's why I wrote it as bar. You can in here, majority of the things are written as bold letters only. Okay, so equality is indicated as vector A is equal to vector B. Okay, note that in figure B. Now let us look at the figure B for once. Okay, so in figure B, what is happening? The vector A dash and B dash have the same magnitude. Okay, so basically the length of these both vectors are same. The length of these both vectors are same, but unfortunately the direction is not same. It can be visualized very clearly from the diagram only that the direction of both these vectors are not same. Okay, so note that in figure B, vector A dash and B dash have the same magnitude, but they are not equal. Why they are not equal? Because they have different directions. Okay, fine. So even if we shift B dash parallel to itself, let us try to understand this why they are not equal. Okay, so let us look over the same scenario again. Let us try to shift B dash. So how will it shift to itself? So that its tails Q dash coincides with the tail O dash of O. So try to put this Q dash on this point O here, and the tip S dash of B does not coincide with tip of B dash. Okay, so basically this will be somewhat like this. Okay, so it is quite evident that this value of tip does not coincide with that of B dash. Okay, so that is why what we can say is that these both vectors A dash and B dash are not equal. How can we write this mathematically? We can write mathematically as A dash bar, if I'm writing it as vector like this, is not equal to B dash bar. Right? So that is how mathematically we can write this concept. Fine. So we understood the equality of vectors also. In the previous slide, we understood what are vectors. In previous slide, we understood how we represent the vectors. In previous slide, we understood what are the position and the displacement vectors. And now in the previous slide, in the present slide, we understood equality of vectors. Okay. Let us now understand first multiplication of vectors by real numbers. Okay. So how multiplication is supposedly done for vector. Okay. So let us understand this scenario here now. So multiplying a vector A with a positive number lambda. So this is called as lambda. So this is lambda. Okay. So just to explain to you, there is no requirement of here. There is no requirement lambda here. This is generally used to explain a concept which is called as wavelength. Okay. So these all things will be understood in future classes. Let's not go into that discussion right now. Just a little bit extra knowledge I explained to you, but that is not required at the moment. So let us take, so here you can understand this as a positive number. So any number is being explained by using a number which is lambda. Okay, so multiplying a vector A with a positive number lambda gives a vector whose magnitude is changed by the factor lambda, but the direction is the same as that of A. Very important line. Okay, so what is basically happening? Let us say we have a vector A. We multiply it by a positive number 2. What happens? The length of this vector gets changed to 2A. If let us take the length of this to be L, then the length of just 1 minute. Okay, let us take the length of this to be L, and the length of this will be equal to 2A. Fine. So that is how it is here. So multiplying a vector A with a positive number lambda gives a vector whose magnitude is changed by a factor lambda, but the direction is the same as that of A. Therefore, what we can write? So we understood that how we wrote magnitudes of vector. We wrote it like this, right? So similarly, what we can say, that magnitude of lambda a. What is magnitude of lambda a? Magnitude of lambda is nothing but lambda times magnitude of a. Okay, so just multiply a factor of lambda into this magnitude of your a vector, and you will find the answer. Okay. So it is also written here that lambda, this is only and only valid if lambda is positive. Okay. What happens if lambda is negative? We will explain it in the subsequent points only. Okay. So for example, if a is multiplied with 2, the resultant vector is 2a, which is in the same direction as a. Quite evident, as you can see clearly in this figure a, that it is in the same direction as a, and has a magnitude twice of mod a. Okay, it has a magnitude twice of mod a, which I just explained to you. Let us take the length of vector a as L, then the length of vector 2a will be 2l. Okay, so that thing is also explained, which is shown in figure a. Next point says that multiplying a vector a by a negative number lambda gives the vector lambda a whose direction is opposite to the direction of a, but whose magnitude is minus lambda times a. So now what happens is basically let us take we have some vector a, we multiplied it by the number -1. What happens is the length would be same only, because -1 into magnitude will give you the same length, right? But the direction would reverse. Please remember, see, as you can see, direction would reverse. Similar direction would have reversed here also. Okay, so in this case, we multiplied a with -1.5. Okay, so that is how the consideration is being done. So if we are multiplying it by a negative number, the direction of that gets reversed. Okay, so the direction, let's say supposedly like this, then it will change it to like this. Let us take it as supposedly like this, it will change it to like this. Okay, so that's how the multiplication by a negative number takes place. Okay, so multiplying by so this thing is explained. Multiplying a vector a by a negative number gives the vector lambda a whose direction is opposite to the direction of a and whose magnitude is minus lambda times mod a. Okay, multiplying a given vector a by negative numbers, let us say -1 and -1.5, gives vectors as shown in figure b. Okay, so there was the example which was being explained here. The factor lambda by which vector a is multiplied could be a scalar. Okay, so this vector could be a scalar having its own physical dimension. So the dimension can be anything, as long as that multiplication has some meaning. Okay, then the dimension of lambda a, and dimension lambda a is the product of the dimension of lambda a. Okay, so let us say this has some dimension. In the previous chapter of units and measurements, we understood that we try to explain or mathematically write the dimensions in square brackets, right? So lambda into this is equal to lambda a. So what does this line say? This line basically says that the dimension of lambda a would be nothing but the multiplication of dimension of lambda into dimension of a. Okay, to understand the dimension concept again, you can just refer to the back lectures of units and measurements. Fine. So this thing is also explained. Next thing is, for example, if we multiply a constant velocity vector. Okay, constant velocity vector. How to write a vector? Let us take this into scenario. I'm writing constant velocity vector like this. So let us say we multiply constant velocity vector with duration, which is time. Then what do we get? We get displacement. Generally, displacement in vector form is written as s bar. Okay, so what we are basically doing here, let us try to take this into example here. So I'm just saying that the displacement of s is nothing but equal to displacement of v into, not displacement, I'm really sorry, dimension of s is equal to dimension of v into dimension of time. We can prove it also. What is the dimension of LHS? The dimension of LHS is nothing but equal to meters. What is the dimension of RHS? So RHS is nothing but, what is the dimension of V bar? It is nothing but meter per second. What is the dimension of time? It is second. So second gets cancelled. It is meter. So as you can see that LHS is equal to RHS. Okay, so that is how the dimension homogeneity is being proved. Okay. Fine. So that was the multiplication of vectors by real numbers. let's move on to the addition and subtraction of vectors. Okay, so now this is a very important topic. Please have a consideration. I will just introduce this topic for now, and then we can understand this in very detail in the next lecture of this chapter. Okay. So addition and subtraction of vectors, graphical method. Okay. So as mentioned in the section 2, that is behind one, vectors by definition, it obeys the triangle law or equivalently the parallelogram law of addition. Okay. So there, what was vector defined? Vector was defined as a quantity which has a magnitude and a direction which obeys the triangle law of addition, or more explain or equivalently parallelogram law of addition. Okay, so let us now understand this law of addition by graphical method. Okay, fine. So we shall now describe this law of addition using the graphical method. Let us consider two vectors A and B that lie in a plane as shown in the figure. So let us take that A is in this way and B is in this way. Fine. So that is to take it into general case scenario. Now the length of the two segments, the length of the line segments representing these vectors are proportional to the magnitude of the vectors. Okay, what does this line say? This line just says that as you can see, if you see it very clearly, you can observe that the length of vector B is greater than the length of vector A. So they are just trying to explain to you scenario that whenever we try to understand method of addition or subtraction of vectors, graphically when we explain a vector, that the length of the vector depends upon the actual magnitude. So we try to represent it graphically. Let us take into scenario that A bar is nothing but having a magnitude of 2 meters, let us say, and there's a vector B which is having the length of 4 meters. Fine. Or let's say I take it into more big number. Let us take this to be 6 meters. Okay, and let us take that both are having same direction, which is towards the x-axis. Okay, so if I draw 2 meters like this, let us take, if I draw A bar like this, then B bar would be actually like this. So that will represent it clearly on the graph. So they are just by this line, this is the explanation being done. Okay, so the length of the line segments representing these vectors are proportional to the magnitude of the vectors. Okay, to find the sum A plus B, we place the vector B so that its tail is at the head of the vector A. Okay, so what is written here? That to find the summation, what do? We place the tail of so that its tail. So the tail of this at the head of A. So we just put this at this location, which is done here. Okay, so we just took B from this position, we placed it at this position. So that has been explained here. Okay, so to find the sum A plus B, we place vector B so that is the tail of B here. This is the tail of B. It is kept at the head of A. So that is the head of A, and this is the tail of B. So we just kept it at this location. Okay. Then as it is done in figure B. Then next thing is then we join the tail of A to the head of. Then we join the tail of A, that is the tail of A, to head of B. Okay, tail of A to head of B is being joined. Okay, so this line OQ is a vector R, which is the sum of vectors A and B. So as you can see, a triangle is being made here, and hence it is called as triangle law of addition. So there is nothing but addition of A plus B, and that is how we add two vectors. Since in this procedure of vector addition, vectors are arranged head to tail. How it is being arranged? As you can see clearly, it is arranged head to tail. The head of vector A and tail of vector B. Okay, this graphical method is called head to tail method. Okay, so everything which is general, 90%, 95% of things which are the definition which are written can be understood even by the name itself. Okay, so it is written here, it is head to tail method. Okay, the two vectors and their resultant form three sides of a triangle. The two vectors, so what are these two vectors? Form and their resultant. This is the resultant, basically resultant is R here. The resultant form three sides of a triangle, and so this method is also known as triangle method of vector addition. So that is how you represent the vector addition. Okay, So that being said, let me stop it here only. In the next class, we will understand two properties of vector addition, and then we will understand subtraction, and then we can move on. Okay. So let me stop it here only. So the course progress. The course progress for you. We started with the introduction. Then right now we're on the scalar and vectors part. The next thing was multiplication of vectors by a real number, and finally right now we are on the addition and subtraction of vectors by graphical method. Okay. So let us understand this topic, and then we can move forward to things concept like resolution of vectors, then vector addition by analytical method. So this is very important concept, and then we can move on to the majority main concept, that is motion in a plane and exam applications, examples of it. Okay, fine. So let me stop it here only for this today. So thank you so much.